Hello, my name is Adam. In this video we are going to learn how to make the classic game Tetris in Unity. Tetris is a tile matching video game created in 1984. In Tetris, players complete lines by moving differently shaped pieces which descend onto the playing field. The completed lines disappear and grant the player points, and the player can proceed to fill the vacated spaces. The game ends when the playing field is filled. The longer the player can delay this eventual outcome, the higher the score will be. This tutorial will utilize some more advanced programming techniques, so if you have never written any code before, then I would recommend starting with one of my other tutorials, such as Snake or Pong. If you need help at any point in the tutorial, feel free to join our Discord community where we can offer direct help. There is a link in the description of the video. Please consider subscribing to the channel to support the amount of effort it takes to create a video like this one. It is completely free, but it helps me a ton. Thank you. Enjoy the video. Let's begin by creating a new project using the Unity Hub. In the top right corner, we can click the blue New button, and specifically we can click the drop down next to it to select the version of Unity you want to use. For this particular tutorial, I'm going to be using Unity 2020.3, which is the current long-term support version, or the latest long-term support version. So Unity 2020.3, and here we can choose our template we want to use, in which case we're going to select the 2D template since this will be a 2D game. This will install various 2D packages, and for this game, the one that's going to benefit us the most is the tile mapping. So we'll select that template, name the project whatever we would like, choose where you want to save your project, and click the create button. And then from here, this might take a couple minutes to initialize, so we'll pick it back up as soon as it's finished. Once your project finishes initializing, it should look something like this. The first thing we're going to do is import a few custom sprites we're going to be using throughout our game. This is absolutely not required, but I'm going to do so just to make our game look a little bit prettier. If you want to use your own sprites, you are absolutely more than welcome. And also, you don't have to use custom sprites at all. Just using a simple square sprite will be completely sufficient for this game. If you want to use just a basic square sprite or any other basic sprites that come with Unity, you can right click in your project panel, create 2D sprites, and then they're square, circle, etc. The square sprite is absolutely all you really need for this game from a simplistic level, but like I said, just because I want to make the game look a little bit better, I'm going to import some of my own custom design sprites. So first, let me create a new folder called Sprites, and then I'll go ahead and drag all of these in. And once again, you are absolutely more than welcome to use these same sprites that I'm using. They will all be available through GitHub, as well as the rest of the source code for the project. There's a link in the description of the video for that. When you open up GitHub, it should look like this. And specifically, the sprites will be found in the assets folder and then the sprites folder. And these are all the exact same sprites that I'm using right now. So here, once we import these sprites into our project, we do need to change a few settings in them. So I'm going to select all of the sprites. And the main thing we need to change is the pixels per unit to 192. All of these sprites are designed specifically at that pixels per unit value. And then from here, we also want to change the filter mode to point. And we can go ahead and apply those changes to all of them. We do need to change a couple settings specifically for the grid, and then that's it. So for our grid here, we're going to change it from clamp to repeat, because this is going to be a repeating grid pattern. And then on that same note, we need to change this mesh type to full rect, which is also needed in order for us to tile this specifically for our grid. So that's it in terms of importing our sprites. Let's do a little bit of scene setup now using some of these new sprites we've added. The first thing I'm going to do is go to our scenes folder here. I'm going to rename this to Tetris. So with that being renamed, on the left here is our hierarchy, which displays all of the game objects in this scene. And if we select one of those game objects, on the right is our inspector, where we can see the components that have been added to this game object and all their values. So for example, this main camera has a transform, a camera component, and an audio listener. So for our scene setup here, we're going to customize this a little bit. First, I'm going to change our camera's background color to match some of the sprites we've imported. So let me grab this color over here. So we can open this up. Let's change our hexadecimal here to 2F353D. Once again, this is, you can customize this however you'd like. This is the color I'm going to be using because it matches the sprites I've designed. If we go to our game view here, we can see that background color has changed. All right. And the other thing I'm going to do is change our size of our camera here from 5 to about 12. You can see this white outline is changing. So by me increasing the size, we're effectively zooming out. We're sort of pulling the camera further back so we can see more area. And so a size of 12 will give us exactly enough space to fill in our entire Tetris game board. So size 12, that's it for that. And let's go ahead and add a couple of these sprites to our scene. So first, let's add our grid. All we need to do is select that and drag it into our hierarchy. And what this is going to do is going to create a new game object, and it's going to add a sprite renderer to that game object with that particular sprite being set. And here we can see that grid object being rendered in our scene. Now, that's just a single, that single sprite. We want this to tile because it's a grid. So we can change our draw mode here from simple to tiled. And then all we need to do is specify a size. So for Tetris, typically the size of the game board is 10 by 20. So I'm going to use that, 10 by 20. There we go. We can see that being drawn there. And let's see what else. I think that's it for our grid. Next, let's go ahead and add our border. So once again, we just drag that into our scene. It already looks perfect. We don't really have to change anything there. That one just renders as is. Once again, if you're using the sprites that I'm using, everything's kind of already designed and set up for you. So it makes the effort a little bit, but these two game objects I've added here are not required by any means. They're more of just a visual aid to the player to show the grid lines and so on, but they're absolutely not needed. So feel free to customize this, use your own sprites, do whatever you want to do, or follow along like I am. Let's go ahead and set up a tile map that we're going to be using to draw all of our game tiles onto. So in our hierarchy here, we can right click, 2D object, tile map, and rectangular. This will create first a grid and then a tile map as a child of that grid. For the grid, I'm going to rename this to board, for game board. And then we have our tile map, and we actually don't need to change any of the settings here. The defaults are exactly what we want for this game. So we are all good there. We do want to change actually one thing. I lied. We want to change their order in the layer here. So by default, it's 0, and it's also 0 for all of our other sprites we've added too. The problem is, or what this does is it determines the order in which things are rendered. And so we have to think about the layering here of our objects. In the furthest position, the most background element should be this grid here, because everything is going to get drawn on top of that. So we want our grid to be 0, then followed by our border will render on top of that. So that can have, well, actually the border will render on top of everything. This will always be, the border here will always be the outermost. So we can, for example, maybe set this to, just any large value really. When all is said and done, our game is going to have 4 different objects. So if we go in order, it'd be 0, 1, 2, and 3. So since this is supposed to be the topmost, we'll just set that to 3, but really it doesn't matter as long as it's the largest number. And then for our board here, our tile map specifically, this will be 2. And later on, we're going to add a second tile map for a special ghost feature, which will be order 1. So basically our grid is 0, followed by our ghost tile map, followed by our main tile map is 2, followed by our border is on top of everything. I suppose we can go ahead and create that ghost tile map right now, although we're not going to utilize it right away. But basically we can just duplicate our current grid here. Now we'll have a second one. I'm going to call this one ghost. And I'm going to rearrange these in the order that rearranging these doesn't matter, but just to make it clear, we have our grid is 0, followed by our ghost will get set to 2 or 1. And then we have our board is 2, and then our border is 3. So 0, 1, 2, and 3. So that's it. We have our tile maps, we have our 2 grids, making sure they're drawing in the correct order, and we're good there. Now let's actually create some tiles. To draw a tile onto our tile map, we need a tile asset, and a tile asset has a sprite associated with it as well as some other data. So if we go to our scene view here, if we select our grid here, our board, there will be this button, Open Tile Palette. So we can click that. And then from here, we can create a new palette of tiles that we can use to draw onto this. So we can create that. I'm just gonna call this like blocks. It really doesn't matter. Blocks, tiles, pieces. I'm gonna choose where to save this. I'm actually gonna select a new folder. So I'm gonna call this tiles. Put that in there. And so there's our blocks asset. And now we can drag in all of these blocks we want to add. So let's grab all of these. Everything other than border and grid, we can add to our palette here. So we just select all those and we drag them in. Once again, we're going to select a folder because it's going to create assets for every one of those sprites. So we're going to select our tiles folder. Boom, it created a tile for all of those. Notice here in our folder, we now have tile assets. And so here, when we select one of these tile assets, it is, like I said, there's a sprite associated with it, but there's other information such as the color, or you can use the color to tint it, and then the collider type and so on. And so these tiles are what actually get drawn onto a tile map. So let's go back, let's open that up again. For example, if I just select any of these, let's say orange, I can literally just draw these on here, right? Now we're going to be drawing these on here programmatically, but it's the same concept and we still need these tile assets in order to do it programmatically. So that's really all we needed to do, is make sure that these assets are created for us, and so we're good now. All right, next we need to set up some of our Tetromino data, or the data for our actual pieces. That's what they're more formally called, as Tetromino, or Tetrominos, plural. There are different shapes, I, O, T, J, S, L, and these are the typical colors you will see for those various shapes. So we're going to set up some data to indicate these shapes. So let's go ahead and first create a new folder called scripts. And we're going to create one called Tetromino. And let's also create a couple others real quick too. Let's create another one for data. And let's create one more for now called board, which is our Tetris board. And so our board script here, we can throw onto our actual tile map. Or not the tile map, but the grid. So this parent, or not the ghost, I have the wrong thing selected, but our grid here for board, the object that's called board, we'll add our script called board to it. And we'll go and edit this in a minute, but first we need to grab some data. We need to actually set up some data for our pieces. Let's open up this. Once you open up a script, oh, here, let me select. So if you're using VS Code like I am, it might prompt you to select one of these projects so it knows how to load. You'll want to select a solution file, that .sln file. So we go ahead and select that. That way I get my IntelliSense and all of that. I'm assuming you have the C# extension working, but you definitely don't need to use VS Code. It's your personal preference, whatever you want to use. So here is our script. When you create a script, by default, Unity creates a class that inherits from mono behavior. For this particular one, we're actually not going to have a class with mono behavior. We're just going to define a custom enum. An enum is like an enumerated list of values. So, and then you provide names to those values. So of Tetromino. And in here, we will list out those different shapes. All right, so let me pull up that Wikipedia page again. And we're gonna just literally have the letters as be our names. You can call them something else if you'd like, but I'm just going to literally call them that. So I, O, T, J, L, S, and Z. So those are our different options. And finally, now we also need to add a custom data structure that's going to store certain data for each of these respectively. So we'll have a data structure called Tetromino Data. And we need to make sure that we can see this data in the editor, right? I'll show you in a minute. Let me actually come back to that. Let's add a couple things to this first. So you have Tetromino Data. From here, we need to select which of these values do we want to associate this data for. So we're gonna declare a variable of this with the same type of our enum, and we can just call this Tetromino. And then we also need to be able to select which tile we want to draw for whatever Tetromino you've selected. So we can define a tile asset here, and actually to use tiles, we need to import Unity engine.tilemaps. Now we can use this class called tile, and we can specify the tile there. So that's our basic data structure. We're gonna flesh this out a little bit more. But now if we go to our board script here, let me clear this out. I always like to kind of start fresh on all of these, so I usually get rid of all the default stuff they provide to you and just kind of start with an empty class, but that's just my preference. We want to define an array of Tetromino data. We need an array of these so we can customize them in the editor. And if this is confusing, it'll all make sense as soon as we see it show up in the editor. So let me finish typing this out. We have an array here, an array of Tetromino data. I'm going to call this Tetrominos, plural. And notice what happens in the editor now once this recompiles. Well, we select our board asset with our board script. You actually don't see anything. Nothing happened. And that's because this data structure can't be serialized and show up in the editor. It doesn't know how to display this data in the editor. So to fix that, all we need to do is add a custom attribute here. We can say system.serializable. And now Unity knows how to serialize this so it can get displayed in the editor. So now here, when I select our board and our script, you see this new array pop up, right? So, or this new property pop up, which is our array that we declared. And we can specify our data for these. So there are 7 different pieces. So let's set the size to 7. And for each of these, we can now say, okay, for I, we need to associate a tile with it. And so let me select each of these, I, O, T, J, L, S, and Z. And we need to assign the corresponding tile we want to render for that given letter. So standard is I is cyan, the O is yellow, the T is purple or magenta, J is blue, L is orange, S is green, and finally Z is red. So completely up to you. You don't have to choose those. You can completely customize them. Whatever tile you want to draw is absolutely fine with you. But that is the standard Tetris setup there. So we've set up our Tetromino's data. So we're actually not quite done setting up our data for our Tetrominos. We still need to define some coordinates that make up the cells of every piece. That way it knows how to actually, form that shape. So let's actually go back to our Tetromino data structure here. And let's add a new property for our cells. This will be an array of vector2. We actually need to import Unity Engine first so we get all the standard data structures that come. So an array of vector2. Actually, it'll be vector2 int. Since this is a 2D game, everything's kind of whole numbers. And, well, it doesn't have to be whole numbers. But For our cells, these will all be whole numbers. So vector2 int, array, we'll call this cells. And so here in the editor now, we can see all of those show up. So for example, for each of these, we can say cells. So we could, we can go through here and manually assign all of these coordinate values for each of our pieces. It would be a little bit tedious to do that. So we're actually not going to do that. I'm going to do this a little bit differently, but you could in theory do it this way. And what is cool about this approach is you actually could define some custom shapes if you wanted to. Using these coordinates, you can completely kind of customize, you can make any shape you want really. And they don't have to be 4 cells. It could be more than 4 cells. But for normal Tetris, and for the sake of kind of time, I'm going to do this a little bit differently. So we have this data class here that we never did anything with. So let's go ahead and actually revisit this, because this is going to just store a bunch of static data that define or that we'll use throughout our game. So let's clear all this out. This is actually not going to inherit from mono behavior. It's just going to be a static class, which means you cannot directly instantiate this class. You cannot create an instance of data. This is just static data that we can access from wherever. And once again, for the sake of time, I'm not going to write it all out because it would be quite tedious. And it's a lot of just numbers that are somewhat arbitrary. And so I'm going to actually copy this from my other project. And I can show you how to copy it from GitHub as well. So I'm just going to copy all of this data class here. And I'll explain what it's doing, but let's copy all this and get this in place. And first, before I jump into that, if you want to copy all this too, you can see here it's just a lot of numbers, a lot of vector2 ints for coordinates. There's these things called wall kicks. There's our cells. There's, it's just a lot of kind of tedious typing out of data. And so this is the one thing where it's like, let's kind of just copy and paste this for the sake of time. That way we can focus more on the actual game logic in this tutorial video. I don't want to sit here and spend 15-20 minutes just typing out all of these numbers. So if you want to copy that, you can certainly pause the video and just kind of type it all out. That's an option. But it would be a lot easier to just open up the GitHub page. Once again, link in the description of the video to the GitHub page. And you can go ahead and go to assets, scripts, and then data, and you can copy this whole class here. It's just a bunch of static data that we'll use throughout the game. So I normally don't recommend people just kind of copy and paste, because then you're not really learning anything. But in this case, I don't know that you'd really be learning anything anyways, just sitting here typing out a bunch of tedious numbers and stuff. So, you have my blessing to just kind of copy and paste this one. So there's all of our data. Now we still need a way to actually pick out and like grab these array of coordinates and assign this value here, right? So for example, our cells is a dictionary. Dictionary is a key value pairing. So here's our key is, Tetromino I, for example, and here's our value, which is our cells. So for every key, for every piece, we specify what array of cells are associated with that. So yeah, we need now a way to actually assign this though, using this static data. So first, let's go ahead and actually just create a public function called initialize. And we can assign our cells here. Oops. Say this.cells equal, and then we can access that data class. And then we can say data.cells. And to look up the particular value given a key, the key in this dictionary is Tetromino, which is our enum that we declared earlier. So we can just say this.Tetromino. And now we're looking up the associated, the cells that are associated with this Tetromino. And now we're storing that into our field here. Oh, and one thing I forgot to do. So this right now would still show up in the editor. We don't need it to show up in the editor. So we're going to change this from being a C# field to a C# property. And to do that, we can just define some getters and setters here. So we can say it's a getter with a private setter. And this will no longer show up in our editor here. So none of those cells show up anymore, which is what we want. Well, you can, if you want to do that approach, you absolutely can do that approach and not go through. You cannot use the static data. Instead, keep this a field, and then you can manually assign the coordinates in the editor, which would potentially allow you to create like custom shapes if you're interested in doing that. But for our standard Tetris, here we have our cells. We're assigning that to, based on the static data, looking up those values using whatever piece you've assigned. So that is it for setting up our data. There is more stuff in here we'll utilize later. You might be wondering like what the heck are wall kicks? That will be used for rotation once we get to it. But one step at a time. We're at a point now where we can finally start to spawn our pieces onto our game board. So let's go ahead and open up our game board script, and we can go ahead and spawn our first piece. Let's first define a function called awake, which is one of the built-in Unity lifecycle functions. This will get called automatically when your component is first initialized. And so in awake here, we actually need to loop through our list of data and initialize all of our data, right? So we had declared this initialize function, but we're not calling it from anywhere yet. So we need to go ahead and call this when our game board is first initialized. So we can loop through for int I equals 0. Can't type. I is less than this tetrominos.length I++. And we can go ahead and access each element at that index and call our function initialize. By the way, for the record, we will be adding more data to this structure, but for now, we don't need anything other than our cells. Using the cells, we can actually properly render things. All right, what else do we need in here? So in order to draw something onto the tile map, we actually need to get a reference to our tile map. So let's go ahead and declare a variable for that. So tile map, we need to first import unity engine.tilemaps. We can have our tile map variable here, and I'm going to make this getter with a private setter, and I can just assign this in here in our awake function. This tile map equals get component in children. If you remember, our tile map is actually a child of the game object that our board script is attached to, so we'll get component in children. So now we have our tile map, which we can use to actually set tiles on and draw our pieces. We've initialized all of our data. And now let's implement our start function. So when our game starts, we can spawn a piece. And we'll have another function here called spawn piece, because there will be multiple places where we call spawn piece. So we want to add all the logic in here, and we'll just simply call spawn piece from start. So in spawn piece, we need to just pick a random element from our array here. I guess it doesn't have to be random, but typically in Tetris, it kind of just picks a random piece. So to do that, we will store a random index into an integer here. And we can use Unity's random class. So Unity has a class called random, and we can say random.range. So it's going to get a random number between a min and a max. And our min will be 0, and our max will be the size of our array, the length of our array. So this tetrominos.length. So there we're getting a random index, and now we can grab the data at that index, this tetrominos, and we'll grab the data at that given random index. Awesome. So from here, we need to actually set the pieces or set the tiles on our tile map. And this is something we'll do quite a lot. So we're going to add a function called set. and we need to provide some data that we want to set in here. We actually need to go and declare another class before we move on to this though. So let's go ahead and go back to Unity here. And let's create a new script just called piece. So this will be like our game piece essentially. And with Tetris, it's kind of nice because you can only control one piece at a time. So you really only need one instance of this. In a lot of games, you would repeatedly spawn a new piece over and over. But in a sense, you really only have one piece you're controlling. And then once it gets locked in place, we can just reinitialize that same piece with different data and and we don't have to like reinstantiate it every time. So we can actually go ahead and go to our game board, the same place where our other script is added, and we can add our piece there as well. And let's go ahead and open up this file and let's add some logic here as well. So as I just mentioned, we're going to use this one piece throughout the entire game, and then it's just a matter of reinitializing it with the correct data every time. So we should probably have a function called initialize where we can pass in the data we want. And so we got to think about what is that data. For one, there should probably be some kind of spawn position, right? So what's the initial position you want to, place this piece? And then also, what is the Tetromino data that you want to use while this piece is active, right? And then lastly, we should pass in a reference to our game board, because our game board, we're going to need to call various functions on the game board during when certain events happen from our piece. So the difference in these two classes is our game board's going to control the kind of general, like overall state of our game. It sees the bigger picture of things. It has the entire tile map, and it can render and set tiles and so on. Our piece is just the individual piece, and this is where we will add logic for like inputs and controls, moving, rotating, etc. But we'll need to communicate back to the game board anytime the piece moves. We need to communicate back to the game board, hey, reset this piece in a new position, etc. Right, so we should also pass in a reference to our game board, and I'm going to add that as the first argument there, or the first parameter. Now we need to store all of these things into variables, so let's declare those. So first we'll have board, and I'm going to declare all of these as properties. So public getter with a private setter. Same thing for the others. We'll have data here. Public getter, private setter. And then finally our position. Vector 3 int. It'll be vector 3 int because tile maps use vector 3 ints instead of vector 2 ints. So position, get with private setter, and we can just directly assign all these one to one. So this dot board equals board, this dot position equals position, and this dot data equals data. Now the one other thing we probably should do is have an array of cells. We're storing the array of cells in our data here. However, we're going to be manipulating those cells per piece. So we need sort of a copy of this data. The cells here defined in our data structure are kind of like the original, the original default state of that piece. But once you rotate it and so on, that will need to be changed. So we really should have an array of cells as well. So let's have, and once again, these were vector 2 ints. Well, so we're actually going to treat these like more like tiles. So they'll be vector 3 ints, an array, and we'll call these cells, and we will get with a private setter, same as the others. And we can assign all of those in here as well. So if that array is null, that's the first thing we need to do. If we've never initialized this array, we should go ahead and do that. So we can create a new array here, vector3 int, and we need to provide the length of our array, which will be however many cells our data has. So this dot data, or we can just say data dot cells dot length, which would be 4. Like, I guess you could hard code it to 4 because every piece has 4, but potentially if you're using custom shapes and so on, like, it would be better to do it this way. It's usually you want to avoid hard coding magic numbers like that. So that's just initializing our array. We still need to populate that array with these cells. So we're just going to essentially copy the data from here into our new array here. So we can loop through for int I equals 0, I is less than data dot cells dot length I plus plus, and we can go and set all of these. So this dot cells I equals let's see, equals data dot cells I. Now this is giving me an error because our cells here are declared as vector2 ints, but here they're going to be treated, we needed them to be vector3 ints in order to set them on our tile map. So we can actually just cast this to vector3 ints. And there, we're good there. Later on, we're actually going to end up changing this a little bit once we implement rotations, but for now, this is fine. So just at least getting the initial structure in place. Cool, so that's like our piece. There's going to be a lot more we add to this, but that's a good start. Let's go ahead and finish our set function. So let's jump all the way back to our board. Let's go to our set function, and we need to provide the piece we want to set. So we can pass that in. We can say set piece. That way we can read the cells that we want to actually set on our tile map. So to do that, we need to loop through every cell in the piece. So for int I equals 0, I is less than piece dot cells dot length I plus plus. And from here, we just need to set the tile on our tile map. So we need to get a vector3 int. We need a position to provide to our tile map. So we'll call this tile position. And this is going to be our cells piece. Oops, forgot my equal sign. But we need to offset this based on the position of the piece. So you can think of the cells as being like, kind of like local coordinates, I suppose, or they're always just, all those values, if we look at our static data here, are like -1. They all range between -1 and +1. So -1, 0, 1. There's actually some cases where it's 2, I think, yeah, for the letter I. But that doesn't give us a sense of like where on the board as a whole is it, right? It could be anywhere on there. So we need to offset each of those cells by the overall position of our piece, right? So it's really each cell plus the position of our piece as a whole. And together that forms like our actual, the actual spot they need to get set. And then finally, we just need to set the tile on our tile map. So tile map, set tile, we provide that position we've just calculated, and then we need to provide a tile to render. And if you remember, we associated all of our tiles with those pieces, right? So we can just pass that in. We can say piece.data.tile. And there we go. That is our function for setting this piece. Now we just need to call this from somewhere, right? So when we spawn our piece, one thing we didn't do is we need to actually, we need to first get a reference to our game piece. So let's add that. So we'll have piece, and I'm going to call this active piece. Same thing. This will be a property with a public getter and a private setter. We can assign that here as well. This dot piece or active piece equals get component and children. Call this piece. And then when we set up our data, so in spawn piece, we pick some random data, and then we need to initialize that piece with that data. So initialize, we need a reference to the board, which is this. We need the position we want to initially spawn this at. So we actually are missing that. Let's come back to that. I'll put some question marks for that for now. And then the data, which is the random data we picked out. So what about the initial position we should spawn this piece at? Well, that's kind of like, it's kind of up to you where you want to spawn that. And so what we can do is we can declare a public field here, and I'll call this vector3 int. I'll call this spawn position. And we can just pass that in here. So we can change this value in the editor and have our piece spawn wherever we want it to spawn. Right? So we're initializing our piece. We're passing in a reference to our game board. We're giving it the spawn position, and then we're passing in whatever random data we picked out. And finally, once we've initialized our piece, now we can set our piece on our tile map. So we can say set active piece, and it will go through, it loops through all of the cells, offsets those by the overall position of the piece, which ends up just being our spawn position, and then we set the tile. Let's go ahead and test this out. I know that was quite a lot of just coding without really testing anything. So let's go ahead and try this out. The one thing we need to do is actually set our spawn position. I suppose for now we can leave it at 0, 0 and just see what happens. And look at that. So there is our piece. It spawns right in the middle because that's 0, 0. I believe, let me double check real quick, but I think the actual position we will want. So you might notice too, it's more, in most Tetris games, they actually spawn more towards the left than the right because most of the pieces aren't perfectly centered. The only piece that can be centered properly are the I and the O, but the rest of the pieces need to either be one to the left or one to the right. Either way, it's going to lean one way. So usually they actually spawn them to the left. So we can actually make our X be -1. Then of course it should spawn at the top of the screen. And that will be, let me undo that. So I changed that value while our game was running, so it didn't actually end up doing anything. So -1 spawn position. Our Y will be towards the top. Now our game board is 10 by 20 as a whole, and 0 being the middle. So we need to spawn it. If we go up 10, that would be the very top. However, our pieces would then, you know, if we want them to spawn within these bounds, we need to go a little bit less than that. And the pieces at the most take up 2 rows. So we're going to do 10 minus 2, which is 8. And that will be a more appropriate value. That said, this can really be anything you want. You know, it's up to you how and where you want to spawn those. Potentially, you can even spawn them out of bounds and have them fall down. Although the particular implementation we'll be using for this video, this works best. So you can see here, every time I replay the game, it's spawning a new random piece because we're just grabbing random, you know, we're just picking a random thing from our array there. And so there we go. There's spawning Tetris pieces. That's a really good start. Let's go ahead and start implementing the movement of our Tetris pieces now. So most of this logic is going to be defined in our piece script. So here we need to start handling input, player input. So to handle player input, we will do that inside of our update function. Update is called automatically by Unity every single frame the game is running, and this is typically where you will do your input. So we can say there will be a few different pieces to this. Let's start simple and then we'll expand upon it. So from a simple perspective, we can say input.get key down. And we can say keycode.a, for example. You can use whatever keys you want. I'm going to use WASD. I think more standard Tetris games use like the arrow keys and so on, but whatever you want, I'm going to use WASD. So we can say A for left, and then otherwise, if you say get key down, keycode.d for right, we need to move our piece. So let's create a function called move. And we need to provide a set of we need to provide a translation, or you know, how much do you want to move? Right, so we can say translation here. This is a vector2 int. You're telling it, hey, I want to move this amount in the X and this amount in the Y. And so here we can say move vector2 int vector2 int left, vector2 int left, and move vector2 int right. And vector3 to vector2. There we go. So we're calling our function move whenever you press certain inputs. And in terms of the actual movement, we basically just need to update our position, right? So we could essentially just say this.position plus equals our translation. However, we need to verify that that position you're moving to is valid, because it could be out of bounds. There also could be another piece there. So how do we handle that? That's what makes this a little bit more complicated. So first, we need to calculate what that new position would be so we can test if it's actually valid. So let's do that first. So vector3 int new position equals our current position, and then we'll increase that. New position.x plus equals our translation, and new position.y plus equals our translation and the respective axis. Great, so we have our new position. We need to test this to make sure it's valid. So we need to communicate back to the game board to know, because the game boards can see sort of the overall picture of everything. So only the game board can really tell us if this is a valid position. So we need to add a function to our game board here, and it's going to return a Boolean, which will be a true or false value. So this will say is valid position, right? And we're going to pass in the game piece we want to test, and then that position we want to test. Vector3 int. So is valid position. In order to test that a position actually is valid, we have to test each individual cell that's part of that piece is valid. Because maybe 3 of the 4 cells are good, but one of them would push it out of bounds or something. So let's loop through all of our cells in our game piece. So int I equals 0, I is less than piece dot cells dot length I plus plus. And from here, we can grab our tile position, just like we did here. We can literally just copy and paste that, actually. We need to get our tile position for that individual cell. Although, it's not going to be whatever the current position of the piece is, because we're testing a new position. So we haven't yet updated the current position of the piece. So we need to not do piece.position, we just need to do this that we're passing into the function. And so there's our tile position. And then from here, there's a couple things we need to check. 1, is it out of bounds? And 2, is there already a tile occupying that space? So to check if a tile is occupying that space, we can just say if this.tilemap.hasTile at that position, well, that means this is an invalid position because there's already a tile there and we can't overlap onto another tile. Okay, we also need to check if we're out of bounds. Now, we haven't really defined what the bounds of our board is. So let's go ahead and add another variable here for bounds, or for board size, really. So we can have vector2 int board size. I can provide a default value here of 10 by 20, since we know most Tetris games are 10 by 20. And now we can actually calculate a bounds. The bounds itself will be a rect int, and we'll call this bounds. And this is going to be a C# property that we compute. So in the getter of our bounds here, we need to first get the position. We need a bounds, you need a position and then the size. So we have the size, we just need the position. And the position needs to be the corner of our board, right? So, because from the corner, then it takes the size and now you have a full rectangle here. So the size or the position of our board initially is 0, right? So we need to offset that by half the size of our, whatever the size we specify is. And by offsetting it by half, it'll put us down into the corner, which is what we'll need. So here we can say position equals new vector2 int. We're going to offset this towards the minimum direction, towards the negative direction. So negative this dot board size dot x divided by 2, and then same thing in the y, negative this dot board size dot y divided by 2. Once again, the position is initially in the center, so we need to offset by half the size of our board to put ourselves in the corner. And now we can finish completing our rect int here, new rect int, and you can see there is a constructor for position and size, which the size we already have just as a variable. Great, so there's our bounds, which we can now add here. So let's get rect int bounds equals this dot bounds. Okay. And we can test if our piece is out of bounds using a built-in function that is provided by our rectint, which is why we did this. I guess I didn't really explain that, but we're using a built-in rectint function that kind of tests this for us automatically. So it kind of just simplifies some things. So we can say if bounds contains some position, which is our tile position. And if it does contain, or if it doesn't contain, so if our bounds does not contain it, which means it's out of bounds, well, now this is also invalid, so we return false. And here it's giving me an error because our rectint is using, it needs to test for a vector2 int, and this is a vector3 int. So we can, once again, we can just cast this to a vector2 int. All right, so that's it. Those are the two tests we need to do, whether it's out of bounds and whether a tile is already occupying that space. If either of those fail, then immediately we know it's invalid and we can return false. If it loops through all of the cells and it never returns false, well, that must mean it is valid and we can return true when all is said and done. So there is our function is valid position. This will be a really important function we'll use in quite a few places later on. So finally, we can go back to our move function in our game piece here, and we can finish this. So we can say, we can check, if it's valid. So this dot board is valid position. We provide this new position that we calculated from the translation. And if that is a valid position, now we can do a couple things. We can set our new position. So we can say this dot position equals our new position. So we can actually go and update that. And one thing that is useful that we'll need later on is it might be useful to also have this function return a Boolean, whether or not the move succeeded. So here at the end of our function, we can just return valid. All right, so we return whatever that got set to. Oh, we didn't pass in all the correct values here. So is a valid position. We need to pass in a piece, which is this, and then our new position. So there is our move function. There's still more we need to do to this, though. We're not quite done just yet, but this is a good start. Let's go ahead and at least test it out. Actually, no, we need to do one other thing before we test it out. Once our piece moves, we need to set it again because it's going to be at a new position now. So we need to recall set. But we can't set it until we've cleared it beforehand because we need to clear where it was previously and then reset it at its new position. So we need to have a clear function as well. So we can literally just copy this set function, paste that in. I'm going to call this clear instead. And the only difference is instead of passing in a tile, we're going to pass in null instead. So it's unsetting the tile. And now we have set and clear. And so for our game piece in our update function, the very first thing we're going to do is clear the piece from the board. So this dot board, clear this. And then once we're done doing any kind of processing, movements, rotations, we will reset it. So we have clear and then set, and all of the actual logic falls in the middle. Now we can actually test this out and see what happens. We do need to make sure, yeah, so board size is set to 10 by 20. I don't think we need anything else. Let's go ahead and try. Yep, so I'm left and right and I can actually move. So there we go. Nice, look at that. Now we can actually also add our move down too. So let's go back to our piece and we can add a move down as well. This is, I think, referred to as a soft drop, because in Tetris there's a hard drop, which is where you immediately fall to the bottom. But there's also a soft drop where you can kind of manually make it fall down one row. So we can say get key down, and I'm going to say S key will be our soft drop. So we can call our move function and this time pass in vector 2 in down instead. And that will make us go downwards. Yep, and so I can like literally move the piece completely now. I can't rotate it yet, but that's kind. It stops me from going out of bounds, so I can't go any further at this point. So all that is working good. The only other thing we could do now is do our hard drop. And that one ends up being pretty easy actually. So let's go back to our piece here. And let's do our hard drop. So let's say if maybe they press the key or the space bar. So let's say space, we can do our hard drop. And for our hard drop, I'm actually going to separate this into a different function just so it's a little bit more clear what's happening. Hard drop. So here we will hard drop. So when you press space, we'll hard drop, and here basically we're just going to continuously move down until we can't move down anymore. So we can create a while loop. While we try to move down, we will continue to move down until we no longer can, right? Because this is where our move function actually returning a Boolean is really helpful. So essentially we're attempting to move down. If this succeeds, it'll return true. Therefore, we enter the body and then we just continue and it repeats again. And then it just keeps repeating so long as it continuously, successfully moves down. As soon as move down fails, it returns false. Well, then our while loop stops and then that's it. There will be a little bit more we add to this function later once we add like locking, but we're not ready to do that quite yet. But now I can press space and it just instantly falls to the very bottom. So that's your hard drop. And there we go. That's a good place to stop and move on to the next section. All right, next let's go ahead and do the rotation of our pieces, which might be the most complicated aspect of Tetris. In fact, there are actually many different ways you can implement rotations for Tetris games. And they even have different systems for doing so. So for example, the current Tetris guideline or standard is to use something called super rotation system or SRS. But there are a number of other ways you can implement rotations. But for my tutorial here, our game is going to be based off of super rotation system. You can see in this diagram here all the different rotation states for each of the 7 pieces. So there are always 4 different rotations for every piece. And also for the I and the O, those 2 in particular are rotated a little bit differently because this little circle here is kind of the center point that it's rotated around. And you'll notice that for the I, it's not exactly on one of the tiles like it is for the others. So those 2 even have a little bit more of a unique rotation, but we're going to go ahead and implement this. It gets implemented using a rotation matrix. So it's actually just calculated kind of on the fly using a rotation matrix. So we'll go ahead and see what that looks like. Let's open up our game piece and let's first add some inputs to actually handle rotation. So input get key down. I'm going to use keycode.q. And then we'll also do input get key down for E. So you can rotate either direction, left or right, and we'll call a rotation function when you do so. So let's define that, rotate, and let's pass in the direction you're rotating. And so up here, when you press Q, for example, we're going to rotate -1, but when you press E, you'll rotate +1. So the way you can think about this is if each of these rotations is an index. So this first column is index 0, the second column is index 1, index 2, index 3, and so on. Here you're basically saying shift down an index or shift up an index to then get to the next rotation. So we actually need to store the index we're currently on. So let's add a variable for that. We'll say public int, and we'll just call this rotation index. And we'll make this a property with a public getter and a private setter. One thing we need to do is make sure we set this to 0 as soon as we initialize this piece. Anytime a new piece is initialized, this needs to get reset to 0. That way it spawns in its default state. Cool, so rotate -1, +1. Let's actually go ahead and implement our rotate function. So for this, we need to update this rotation index, apply our rotation matrix to all of our cells, and then later we will do some wall kick tests, which are, I'll explain those when we get to them, but at the very least, we need to set this up. So let's say this.rotation index plus equals the direction. However, this is actually immediately causes a problem because there are 4 indexes, right? 0, 1, 2, and 3. If you're already on 3 and then you rotate to the right, it would go to 4, but that's out of bounds. That's an invalid index. And so it needs to wrap back around to 0. And let's say it's the opposite. If you're on 0 and you rotate left, it would be -1. That's also out of bounds. So it needs to wrap back around to the other end. So there's a very common utility math function for this called the wrap. And I'm just going to kind of copy that into our project here. I'm kind of skimming over the details of how this math works just for the sake of time, because I think I literally could spend 10 to 15 minutes just explaining how this wrap function works. But it does use some modulo operators to, make sure it wraps to either end of the range based on whether you're below the minimum or above it. So this is a standard utility wrap function. And so instead of just directly increasing our direction, we need to wrap it. So we're going to say wrap this rotation index plus our direction, and we're wrapping it between 0 and 4 because there are 4 possible rotations. Now from here, we just need to apply our rotation matrix. So now this is where the math for this gets a little bit complicated. Like this, at this point, it's really just math. So I'll try to walk through it and explain it the best I can. But we need to apply this rotation matrix to each cell in our piece. So let's loop through all of our cells. This.data.cells .length. Oops. I++. And first we need to just grab the cell itself. And these are vector 3s, or well, those are, let's not do data. We actually want to, if you remember, we have a copy of the cells that's unique to this piece. And this is why we did this, because now that we're rotating them, these cell data is going to start to differ from the source data. So we have a copy of our cells, so we don't want to loop through this.data.cells. We want to just say this.cells. And these are vector 3 ints. However, we actually need these to be just vector 3, not int, because the I and O that I mentioned, those two rotate differently. And the way they rotate differently is that we offset the position by half a unit. And so once we offset it by half a unit, we now need floating point values. And so if we use integers, then it's going to cause problems. So we're going to grab our cell here as just a vector 3. And let's declare two variables x and y that will become our new coordinates after it has been rotated. And now we can apply a rotation matrix. However, once again, I and O are rotated a little bit differently than all the others. So we need to make a switch statement to make sure that we can apply different logic based on which letter is being rotated. So we can switch on the Tetromino, I can never say that. And we can say if it is I or if it is O, we'll do one set of logic. Otherwise, we'll do a different set of logic for the default case, which is every other case, right? So let's actually start with the default, and then we can see how I and O differ from that. So to apply our rotation matrix, this is, if you've learned this in school at some point, this is a pretty standard thing. Basically, we just multiply our x and y component wise, using cosine, sine, cosine, etc. In that data class that we set up earlier, we actually have our rotation matrix defined already for us. So we just need to use each of these values in the array and multiply them with our cells. So what that'll look like is int x equals cell.x times data.rotation matrix, and then the first item in our matrix. And now we're also going to times it by our direction here. That way you can either rotate, it can be sort of an inverse rotation matrix or not, depending on which direction. Okay, and then we add so let me wrap this in parentheses so it's a little bit clear. Okay, now we're going to do the same thing to our y coordinates, cell.y times data rotation matrix. Now we're going to use the second element, or the second value in our matrix, also times it by our direction. And that's our y. Ignore the error for a second. I'll explain why it's giving us an error. Same thing, cell.x times data rotation matrix. Now the next one would be value 2, or second index, not value 2. Cell.y times data rotation matrix, and then finally the third value, or the final value in our rotation matrix, and also multiply that by direction. So x equals cell x plus cell y, y equals cell x plus cell y, and then multiplying by each of the values in the matrix. Now this is yelling at us because it's trying to convert from a float to an int, and so we need to round all of these values. Oh, also I just realized I meant to put this down here. I said we were going to do the default first, so this actually is the default. I just typed it in the wrong spot. So we need to round these all to integers. So we'll round out all of this, and then that is it for our rotation matrix. All right, that's all good now, right? Yep. Oh, I don't need to re-declare those. So we already declared x and y there, so we can just assign them here, x and y. There we go. So that's it. Now let's copy this for I and O, but it's going to change a little bit. So first, before we actually do that, we need to offset these points by half a unit. So we will subtract half a unit from each one. This should be cell.x and cell.y. So we're subtracting kind of the cell position by half a unit because it rotates around a different point. And then also, instead of rounding to int, we need to seal to int instead. Sealing rounds upwards. It always rounds upwards, whereas like normal rounding will, round down or up depending on if it falls below the midpoint, below or above the midpoint. So we offset by half a unit and we seal instead, and that's the difference between those two. Now we have our new rotated coordinates. We just got to assign them back to our cells. So after our switch statement, we'll say this dot cells I equals new vector 3 ints x, y, and then z is 0. And there we go. Let's test that out. All right, let's run. Got a piece here, so I'm gonna press E, so it rotates to the right. Great. Let's see if I can rotate the opposite way. Yep, I can rotate both directions, so that looks good. And if I'm lucky, we can get one of the other pieces that rotate different. Either I or O. If this takes too many tries, I'll just stop, but come on, give me an I or an O. All right, two more tries. Keep getting the red one. Nope. All right, well, forget it. I'm just gonna assume that is working correctly. Later on, as we continue to build out the game, we'll know for sure if it's not working once we're able to play the game in full. But that is our rotation. There is one problem, however. Let me show you. Oh, here, I got the one I was looking for. Let's make sure this one rotates correctly. Yep, it still rotates correctly, so that's good too. Awesome. Now let's try this problem. There's a way to kick yourself. Yeah, so see, I'm getting out of bounds. That's the point of wall kicks. So when you're up against the edge and you rotate, you need to kick off of the wall to reposition yourself in bounds. And so that's what we're going to focus on next. All right, so let's go ahead and implement our wall kicks. Let's open up our game piece script. And down below, where we have our rotate function, we need to add some additional logic in here. So after we have applied our rotation, we need to test various wall kicks. And there are actually 5 different tests for... Here, let me just show you this graph. It'll make more sense. So there are 5 different tests, but the values you test are different depending on which rotation you're doing. So if you're rotating from index 0 to 1, you do these 5 tests. From 1 to 0, you do those 5. So it ends up being 8 times 5 different combinations. So it gets a little crazy. And then unfortunately, I has their own unique set of tests. And earlier when we went and created our data or set up our data class here, all of that, this entire exact data set is included right here. That's what all of this information is. So we have the data. We just need to use it, basically. And the first thing we need to do is we need to add some of that data to our Tetromino data structure here. So, because we need to be able to associate which wall kick to which set of wall kick data do we need to use for this Tetromino. Right? Because unfortunately, I is different than the rest. If it was all the one thing, then it would be even easier, but unfortunately it's not. So let's first start by adding a new field or a new property here for vector2in, and this is a 2-dimensional array, right? It's a table of data, so it's 2-dimensional. We're just going to call this wall kicks. It'll be a public getter, private setter. And we're going to initialize this pretty much the same way, where we can just say now data.wall kicks, and we can look up the correct set of wall kicks based on that. And so that's it in terms of initializing the data. Once again, earlier in the video, we kind of just copied all of this data set from GitHub. I mean, you could manually type it out, that's fine. When I just went through and took all these coordinates straight from this table and plugged them in here. So it's just very tedious to do so. But so once we've added that, we can go to our rotation code in our game piece here, and we can start to utilize this. So we need a function that can actually test these wall kicks. So let's add that. And our function is going to return a Boolean. So it's going to return like a pass or fail, or true or false. Test wall kicks. We need to know which rotation index we are currently on. And we need to know which direction we're rotating. So we're going to pass those in as parameters. And then let's see, test wall kicks. So from here, we need to figure out which of these values in the table we need to test. Are you going from 0 to 1 or going from 1 to 0? Which index are you doing here? So that by itself is kind of its own set of logic that we'll put into its own function. So we'll have a new function in here that's going to return an integer. It's going to say get wall kick index. And we're going to pass in these exact same two things. We'll pass those in. And that'll be the very first thing we do in our test wall kicks is we need to know which index. So that way we know which test to run. So get wall kick index, pass in those same values. Great. All right, so let's actually implement this function here. So when I was first figuring out how to calculate this index, I noticed a pattern. And so we can do a little bit of pretty simple math, actually. All we need to do is need to multiply our rotation index by 2. And then if you are rotating, like decreasing the index, we need to subtract 1. Because so you notice there's like index 0 is going up 1, and then we skip 1 and then go to the next is going up, and then we skip and go to the next, and then we skip, and it goes to the next. Now, if we're rotating the opposite way, that's where, you would increase by 2 or multiply by 2, but then subtract 1. That's probably everything I just said is probably like, you're probably like, what the heck did he just say? I don't understand, but how this specifically works doesn't really matter. It's just like a pattern that I noticed that simplified how we can look this up. So wall kick index is going to be rotation index times 2, and then if you're rotating negative, we have to subtract that by 1, and that is our value we need to return. However, it can be out of bounds, just like our rotation index up here. So we need to wrap this as well. So we're going to use that same wrap function, and we can say wrap the wall kick index between 0 and then the length, which is going to be 8. However, instead of hard coding that, we can say this.data wall kicks get length of 0, just in case for whatever reason this were to change in the future. We don't have some magic number floating around that causes problems. All right, so that's getting our wall kick index. That's once again essentially telling us which of these things do we need, which of these data sets do we need to test. All right, and now we can go and perform those 5 tests. So here we're going to create a loop for int I equals 0. I is less than this.data wall kicks get length in the other dimension. So instead of the dimension 0, we're going to get dimension 1, which are our 5 tests. And we're looping through those. Each of these tests is defining a translation, like a movement, right? It's trying to see, okay, first test, the first test you'll notice is no movement. Did you rotate? And if that's a valid position with no movement, then great, awesome, we stop there. If that fails, we move on to the next test. Okay, let's try to shift the piece over 1 to the left. Does that work? If that works, great. Otherwise, nope, we got to continue to move. So you run through each test, and if all 5 fail, well, then you have to, then that rotation as a whole fails, and we actually need to revert everything we did here. But to test if our translation works, first let's look that up in our wall kick dictionary here, or not our dictionary, but in our 2-dimensional array. So we're grabbing the translation from our data set here, using the wall kick index and then the test index, which is I. And now we can just try to move, right? We can just try to call our move function, which once again returns a Boolean of whether or not that movement is valid. And so if this works, then great. If that succeeds, then we can just return true immediately. We don't even need to test the rest of the things because we're good. We're already in a valid position. If it ends up looping through all of these and it still hasn't returned true, then that must mean the thing as a whole fails. So we return false. Great, so that's our testing wall kicks. Now we just need to actually apply that in our rotation function. So we need to, so after we're done rotating here, we apply our rotation matrix, then we need to do those wall kick tests. If test wall kicks, if that succeeds, Or really, if it fails, we need to revert everything we just did. So let's structure this code a little bit differently to make it a little bit simpler. For one, I'm going to take all of this rotation matrix code, so this entire for loop, I'm going to put that into its own function. So I'm going to call this apply rotation matrix. We paste that into its own function. It needs this direction there, so we'll still pass that in. Okay, and so here we can say apply rotation matrix in whatever direction, you know, you're rotating. And instead of immediately storing our rotation index here, or before we update our rotation index, we need to store whatever our current one is. That way, if this ends up failing, we can revert back. So let's keep our original rotation is whatever it currently is, and then we'll update it. We'll apply our rotation matrix, and then we do our wall kick tests. Okay. If our wall kick tests fail, oh, and what do we need to pass in here? We need to pass in the rotation index, and we need to pass in our direction. Okay, so if these fail, we need to revert back. So we can revert our rotation index back to what it originally was. And then we can apply our rotation matrix again, but in the opposite direction. So we'll negate that, and now it's the opposite direction. And that is our wall kicks. Let's go ahead and test it out. And we're not going to test out every single scenario because there's like 40 different scenarios. Plus there's different scenarios for the eye, but I know right here, if I rotate to the left, you know, it wouldn't allow that because it would push me out of bounds. So here it's good. I'm not getting pushed out of bounds at all. No matter how much I rotate, I'm not getting pushed out of bounds. Let's try a different shape or a different piece. Yep, so great. It's not, you know, it won't, I can no longer like, you know, rotate myself out of bounds. So that's all looking good. That is our wall kicks, which is a pretty neat thing in Tetris that you might not even realize that it's something that's happening, but it indeed is happening. Next up, we need to implement steps and locks. So a step is when the game forces your active piece to step down to the next row without player input. And eventually that means your piece will reach the bottom of the board and then it will lock into place. The other thing with a step is that this is how you introduce difficulty to your game, is we can control how quickly that happens. If it's really quick, then your pieces are going to fall to the bottom of the board really quickly, which gives you very little time to make decisions of where you want to place them. So if you add different difficulty levels to your game, or if you just add levels, usually what they do is that step time gets progressively shorter or quicker, however you want to think about it. That step time becomes quicker and quicker in order to increase the difficulty as you progress in levels. So both steps and locks are related, and they're both going to utilize a timer. So let's create a few variables for this. So first, we're going to have our step delay, and let's say by default it is 1 second, which I do believe is the like a level 1 in Tetris. Like the first beginner level is like 1 second delay, so it's actually pretty slow. And eventually, once you're at like level 15, it's really quick. But you can actually implement that yourself, or you can customize this value however you see fit to your needs or desires of how you want your game to be. The other one will be our lock delay. And let's say this has a value of ½ second. I believe most Tetris games use ½ second, but once again, both of these are customizable. You can edit them in the editor if you would like. Now we need a couple of private fields here. One for our step time and one for our lock time, which should both be floats. All of these are floats. And so the first thing we need to do is initialize these values as soon as our piece is initialized. So our step time will get set to time.time. This is how you access the current time of your game, plus whatever our step delay is. So in other words, this is saying we want our step time to be, 1 second later than whatever our current time is. So, and then for our lock time, this one's going to be a little bit different, where it's going to actually just start out at 0, and it's going to increase, and eventually once it exceeds our lock delay, then that means our piece needs to lock into place. So really what this is doing is it's saying, as long as your piece is inactive, we're increasing this timer. And if you'd make an active move, like a rotation or a just movement, then our lock timer will get reset to 0. So why don't we actually go ahead and do that? So in our rotate and move functions, we can reset that. So for example, in move, assuming that movement is actually valid, we can set our lock time to 0 again. So it gets reset. And this actually works for rotation too, because if you remember, our rotation function does these wall kicks, and our wall kicks actually do a movement. So by adding this here, it actually applies to both movements and rotations. And so this will get reset our lock time anytime you make an active move. Now we need to increase our lock time in our update function before we do anything. And to increase our lock time, we just say lock time plus equals time.delta time. Delta time is the amount of time that has passed since the last frame was rendered. And we want to do this before all of this other code, because then if you end up rotating or moving, it would get set back to 0. Now for our steps, we need to actually check our current time, and if our current time exceeds whatever we set here, then we need to call our step function. And we're going to do this after everything else. So if time.time, so our current time is greater than or equal to whatever our step time is, well then we need to call our step function, which we haven't added yet. So let's go ahead and add our step function here. First thing we want to do in our step function is actually set our new time again. We need to push that time further into the future again. So we say this.step time equals our current time plus our step delay. So it's the exact same line of code we wrote up here. We're just pushing that time further into the future, by 1 second or however long your step delay is. That way this will get called again in 1 second. And then after it's called, it just keeps getting called over and over and over again every 1 second, or however long you set this to. In terms of the actual step, all we really need to do is tell our piece to move down. So we just call our move function and say vector to int.down. And then finally, when we perform a step, this is where we will check for a lock. So we're only going to check for a lock when we actually step. So here we can say, if our lock time has exceeded the amount of time we've specified it can be inactive for, well, then it needs to lock into place. So we'll call our lock function. Let's go ahead and add our lock function. Oh, I mistyped this. This should be this.lock time is greater than or equal to our lock delay. There we go. Lock time is greater and equal to our lock delay. Then it locks into place. When it locks into place, we need to just set the piece on our board. So we say board.set this piece. And then we need to spawn a new piece. So we can call our spawn piece function we added earlier. And there will be one other thing we do in here, but we will come back to that in another section. The other thing too is in our hard drop function, it should instantly lock in place. So we can also call our lock function from here. And I believe that is it. So we created some variables. We initialize those when our piece is initialized. In our update function, our lock time will always increase, and then it will get reset in any rotation or movement. So that's happening here. It gets reset back to 0 anytime you do an active move. And then for our step time, This one works differently, where we just check our current time, and if that exceeds this value here, then we call our step function. Then that time gets updated again. We tell our piece to move down, and we also check to see if we should actually lock the thing in place. Now you might be wondering, if we call a move here, which resets the lock time, won't this never get called? Because then our lock time will always be 0, and it'll never exceed our lock delay. No, because eventually our piece hits the bottom of the board, which prevents it from moving down. So our move down will actually fail, and therefore our lock time won't get reset. And so then this will eventually get called. And let's go ahead and just test this out and make sure it all works correctly. And once again, we can customize those values here in our editor. So if we want, you can play around with those. And once again, our step delay, importantly, is how you can increase the difficulty of the game. And I'll show you that. So right now, I'm not pressing any inputs, and our piece is moving down automatically. I can still go left and right, and it'll still just continuously go down. Let me help it get to the bottom a little bit quicker here. And once it gets to the bottom, it's going to take half a second, and then it locks into place. And then a new piece spawns, and now I'm controlling this piece. If I hard drop this piece, boom, it instantly falls, and it instantly locks in place, and a new piece spawns. Now notice here, if I have a piece at the bottom, just because it's reached the bottom of the board doesn't mean it just locks in place right away. As long as I am making an active movement, I can still control this piece, but as soon as I stop making an active movement, it will then lock in place. And this is useful, and this is actually a really good example, because this allows me to then shift the piece over and underneath our green piece here. And then I'll stop moving, and it finally locks into place. So that's exactly what I want. Now notice here, if we decrease our lock time, let's say to 0.1 second, these are falling much quicker, which makes the game a lot harder because I have very little time to think about and plan out my moves. And this is actually will get even quicker at higher levels of Tetris. So there we go. It actually feels like I can play the game now, which is pretty neat. Alright, so at this point, we're actually very close to finishing our game of Tetris. The only real thing missing is being able to clear lines as you fill them up. And so anytime a piece locks into place, we need to test to see if each row is full, and if that entire row is full, then it needs to get cleared, and then everything above it needs to shift down. We gotta sort of do this, not recursively, but we need to make sure we're iterating through every row in the correct way, otherwise it won't work correctly. So let's open up our board. This is all going to be happening in our board script. So we can add some functions here for testing or clearing lines. So let's say this is a public function called clear lines. And we just need to call this from one place in our piece function. So I mentioned anytime a piece locks into place, that's when we're going to try and clear any lines. So we'll just call that. And we want to call that in between set and spawn. So we set our current piece, then we try to clear all the lines, any lines that can be cleared, and then we spawn the new piece afterwards. And so from here, for our clear lines, we need to basically loop through every row in our tile map, and then determine if every column is full, if there's a tile set in every column, and if so, that means that entire row is full, which means we need to then clear it and then shift everything down. So there's a few different things happening, but it's actually somewhat straightforward. To iterate through our rows, let's declare a row value here. And we want to iterate from the very bottom row to the top. So we can utilize our bounds for this. We established these bounds earlier, rect int here. So let's grab our bounds here. Bounds equals the set bounds. And we're going to start at the very bottom. So all we need to do is say row equals bounds.ymin. And then we can loop from ymin to ymax. And we'll do this in a while loop. So we'll say while row is less than bounds.ymax, we're going to continuously check for a line clear. So first we need to check, is this row full? And we'll handle all of that logic in a different function. So this will be this function will return a Boolean and we'll say, is line full? We'll pass in the row we want to test. And this is now going to iterate through our columns now to verify if the line is indeed full. So for this, we also need our bounds. So we'll grab that again. And we can set up a for loop to say, I'll call this column, and we'll say column equals bounds.xmin. And then so long as our column is less than bounds.xmax, we will increase our column. So we're iterating from left to right. It doesn't actually matter whether you go left to right or right to left. And we're going to grab the position there. So the position of that column. So will be a vector3 int. And the column is our x coordinate. And the row that we passed in is our y coordinate. And then our z is just 0. We're not utilizing z, but it needs to be a vector3 because that's what tile maps use. And here, all we need to check is if our tile map has a tile set there. So if this .tilemap has tile at that position, that means it's good and it should move on to the next column. So really what we should do is say if there's not a tile, then that means this line is not full. If there's not a tile there, we immediately know this line is not full and we can just return false right away. And so if it ends up looping through this entire thing without ever returning false, then that must mean every tile has been set and therefore we can return true. And so that's what we want to test here. While we loop through all of our rows, we first want to check if this line is full for the row we are currently on. Well, now we need to do a line clear. All right, so let's add another function for line clear. Now and we'll come back and implement that in a second. Let's just finish this. If the line is not full, well, then we need to iterate to the next row so we can increase the row. And now there's an important thing here. If we do a line clear, we do not iterate the row. We only iterate the row in the case that it's not full. And that's because once we do a line clear, everything above will fall down, which means we need to retest the same row again because it's actually going to have new tiles on it. So we only increase when it's not full. So finally, let's finish up our line clear function here. This basically needs to do very similar things to what we've done here. We're going to need our bounds again so we know how to loop. And we're going to do the same exact for loop for our column. So I actually just copy that. So we have the same for loop of looping from the xmin to our xmax. We're going to grab our position the exact same way. So I'm going to copy that line of code too. And then we just set our tile map set tile at that position to null. Right? So we're clearing the tile from that at that position. Oh, and we need to pass in the row to our line clear function. So let's pass that in. And then let's pass that in here. There we go. So that's the first thing, is clear all the tiles from that current row that is being cleared. Makes sense. The harder part is having every tile, every row above this one fall down. So let's establish another while loop here. While row is less than bounds.ymax. So this is the same while loop we did up here. While row is less than bounds.ymax. And then for every row now, we need to once again iterate through every column in that row. So we'll have that same for loop. And for every column, we once again need to get the position of that tile. And now in this case, we actually want to say row +1 because we're grabbing the row above it. We're grabbing the tile above this row, and then that tile will get set to this current row. And so here we can say, we can grab what that tile is too, because we need to get what that tile is and then just set it with the same value. So here we actually need to declare a tile base, and I'm going to just call this like above. So this tile is the tile above, and we'll say this dot tile map get tile at that position, which once again is the position at the row above us. Now that we have that tile, we can change our position back to just being our current row. So column row 0. Instead of row +1, it's just our current row. And now we can set our tile map, this dot tile map, set tile at the position using the same tile that is above. So we'll pass above in there. And great, so, and we're doing that for every column and every row. All that's missing is we need to increment our row here. So we'll increment our row. And that's actually it. And that, in a sense, completes our game too. We're actually going to do a little bit more, but this is now a fully playable game. At least it should be. Let's play the game a little bit and test this out. So here I should get a line clear, which it did. Nice. Let's play a little bit longer and make sure everything's still good. I should get another line clear here. There we go, that line cleared. And you can see how things get shifted down as the lines clear. Here we go, and this time it'll clear 2 lines, so we should be left with orange, 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 green, red, red in the bottom. And there we go, orange, 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 green, red, red. So there we go, everything is working. We have a fully playable game of Tetris now. One thing we can do really quickly, because it's only like 1 or 2 lines of code, is a very simple game over state. So let's go back to our board script. All we need to do for game over is when a piece spawns, when that piece spawns, it's already in an inactive position, or sorry, in invalid position, well then that means you've gotten a game over. Right, so as soon as we spawn our piece, or we'll initialize the piece, and before we set it, we only want to set it if it's actually valid. So we can say if this is a valid position, this active piece that we just initialized at our spawn position, oops, this dot spawn position, then we're good. We can set the piece. Otherwise, if it's not valid, well, you've got a game over. So we call a game over function. Let's go ahead and add our game over function. Game over. And just for the sake of time, I'm not going to really do anything fancy in game over. All I'm going to do is clear the entire board so it starts fresh again. So I can just say this dot tile map, clear all tiles. And that's it for now. You very much can do many other things inside here. For example, you might want to load a game over menu, display some game over text or some UI. Just for the sake of time, I'm not going to do any of that. But at the very least, I'm going to clear the entire board so we can basically start playing again from scratch. And that's it. That's our game over. We can test this really quickly by just spawning and letting pieces drop instantly. So I'll just hard drop all of these pieces. And as soon as I reach the top, so boom, yep. So at that point it failed. It tried to spawn a new piece, but it couldn't. And therefore I get a game over and clears the board. So at this point we could stop. This is a fully playable game of Tetris with all the game logic in place. I do want to add one more thing though. In a lot of Tetris games, you'll be able to visualize where your piece is going to land before it actually hits that spot. So they call these like ghost pieces. So while your piece is at the top, you will see like a sort of ghost version of it at the bottom to indicate exactly where it's going to fall. So let's go ahead, and we even created that tile map in the very, very beginning of our tutorial. We just haven't done anything with it. But let's go ahead and actually implement our ghost piece. So let's go ahead and create a new C# script. I'm going to call this ghost. And we're gonna honestly just be copying a lot of the code we've already written. So this shouldn't be too bad. Let's start fresh here. We do need to declare a couple new variables. For one, we need to establish which tile we want to render for the ghost piece. And I need to import Unity Engine tile maps in order to declare this. So we'll establish our tile. We also need a reference to the main game board that we will be tracking. And we also need a reference to our main game piece that we will be tracking. I'm gonna actually call that tracking piece. Then finally, we need a reference to the tile map, not for our main board, but for our ghost board. So we'll have a tile map here. And this will be a property. So this will be a public getter, private setter. And then finally, very similar to how we have our other game piece, we need to have a copy of the cells. So we can have that exact same thing. And we also need our position. So same thing as well. Finally, let's establish a couple of these references in our awake function. So here we can say private void awake. We can establish our tile map by saying get component in children. Tile map. And then our cells, we can initialize that array. It can be a new vector3 int array with 4 cells. I'm just going to assume 4 cells. You might need to do something different here if you're doing like really custom shapes for your Tetris game, but that's a very uncommon thing. Now, in terms of the logic we need to apply to our ghost, there's really kind of 4 steps to it. First, we need to clear the piece. Then we need to copy the cell data from the piece we're tracking. Then we need to drop the piece. We need to basically simulate like a hard drop. And then we need to set it. So let's establish those 4 functions. We have clear. We have, I can't type right now. We have copy. I am completely failing at typing. We have, let's see, clear, copy, drop, and set. Clear, copy, drop, and set. And we're going to call all of these in order inside of late update. Late update is a special update function that gets called after all other updates. And that's important because you know, we're handling some game logic in our main update function for our game piece, but our ghost piece needs to track this. And so if we've done a movement, we need to make sure our ghost piece has, is tracking that correspondingly. Therefore, we need to make sure our ghost updates after our main piece. And so we can just do this in late update to make it easy. So we'll call all of these functions in order: clear, copy, drop, and set. And now clear and set are really simple because those are the same thing we've done for our board, our game board. We can literally just copy this. Our set function here, we might need to change a couple things. What we're changing here is it's not going to be piece.cells, it's just going to be, all of this is just going to be this. So this.cells, this.position, and then instead of this.data tile, it's just this.tile. So we loop through all of the ghost pieces cells, and then we get the tile position for our ghost piece cell and position, and then we set the ghost piece tile. And then for clear, same exact thing, we can copy that. All we need to change is instead of setting the tile, we null out the tile to clear it. For our copy and drop here, copy is pretty straightforward. We're going to establish the same for loop where we loop over all of our cells. And we just need to assign our cell data to be equal to our tracking piece data. That way if we rotate our tracking piece, our cells here for our ghost piece will get updated too. So we said this dot cells I equals this dot tracking piece dot cells I. And that's it. Oops, I didn't mean to do that. That's all we need to do for a copy. And then finally, there's drop. This is the little bit harder one. It's essentially simulating our hard drop that we added in our game piece. So on the right here, we have our hard drop, but really this is calling our move function. So now we have to like basically re-implement a move function, which can get somewhat complicated. But unfortunately, we got to do that. So let's add vector3 int. First, we just need to get the current position of our tracking piece. So position equals this dot tracking piece dot position. And from here, we need to basically loop. We need to loop through every row in our tile map, in our board, like the actual board tile map, and from the bottom to the top. And as soon as we find a valid position, then we know we can put our ghost piece there. If it's not valid, well, then we can't place our piece there. So to establish our loop here, we need to know what our current, we need to keep track of what our current, row is going to be. So the current row we are on, or the current row our active game piece is on, is going to be position.y, right? And then let's establish a variable for our bottom of the board. So we need to calculate the bottom of the board here, which is going to be negative this board size divided by 2. So if you remember from earlier, positions are in the middle of the board, so we need to get half of that to offset by half, and then we're going in the negative direction, so it puts us towards the bottom of the board instead of the top. And then we actually need to subtract 1 from this. We need to push it 1 lower, so we will subtract 1 more from that value. Oh, and then this should be board size.y. We only care about this in the, for the bottom, it's the y-axis, so .y. Now we can go ahead and actually loop through all of our rows here. So for int row equals current, so the row we're currently on. Then as soon as our row gets to the bottom, and notice here we are looping actually more so from the top to the bottom. In some of the other loops we've done, we've usually looped from bottom to top. But in this case, we're looping from wherever our piece is on the board to the bottom, because we're simulating it dropping, so it's falling to the bottom. So we have to decrement our row here. It needs to decrease every iteration. And our position here, we can change its y. So we can say position.y equals whatever this new row is. At which point we can test if that position is a valid position. So we can access our main game board and call our isValidPosition function. So we need to pass in our piece here first, which is our tracking piece. Pass in that position we want to test. And if this is a valid position, then we can update our ghost piece's position to it, right? So essentially, yeah, that spot is free. For sure, our piece will be able to fall to that position. Therefore, we know our ghost piece should get set there too. And if it's not a valid position, then we stop there. We can't go any further. We're going to prevent any more rows from being tested, because that is now where the piece will drop if you were to do a hard drop. So to stop our for loop, we can just break out of it. We just call break. Now, the one thing that's actually missing here, this will cause a problem when we check if this is a valid position. This is going to cause a problem because we're checking, let's say we're starting at the position of the piece we're tracking. This will say this is going to return false because that very same piece is occupying that position, and therefore, it thinks it's invalid. So what we need to actually do is we need to clear the tracking piece from the board before we loop, and then after we loop, we can set it back. Right, so all we need to do is say this.board.clear our tracking piece from the board, and then we'll set it back after we're done doing this test. And once again, the point of this is because if we don't do this, isValidPosition is going to continuously return false, because that very piece is already occupying the position we're trying to test for our ghost piece. And so we clear it from the board to pretend like it doesn't exist. That way we can check all the valid positions without any interference. And finally, once we're all said and done, we'll add it back in the same position it was before. So that's it for our ghost. Let's actually test this out. Let's add this ghost script to our ghost grid here. Let's establish some of these references. So for our tile, I'm going to use the ghost tile that we established. For the board, I need to reference the main game board. So I drag that in from our hierarchy over here. And then I also need to reference our game piece. So I'm going to also reference that in, or drag that in to reference it. And let's go ahead and test this out. So there you go. So you can see at the bottom, that is our ghost piece down there. It's mimicking our current piece, just, you know, pretending like it was dropped all the way. Even if I rotate, it still gets updated and everything is good there. And so this is a lot better. This just really helps the players to better understand what moves they're actually making, because sometimes there can be a little bit of a disconnect between the piece being at the very top and you trying to visualize where it will fall into place. So this just really helps. This definitely isn't required, but it's in most Tetris games you will see some implementation of this. So, and that actually completes our Tetris tutorial. There's nothing else we really need to cover in this video. There are more things you can do, so I would challenge you individually to see how you can implement maybe scoring, as well as a difficulty curve, right? So how can you increase this step delay to be faster and faster as the game progresses, so it gets harder and harder. Those are a couple things that I will let you guys try to experiment with and try to implement on your own. I really appreciate you watching this tutorial, and I hope you learned a thing or two along the way. Give the video a thumbs up or down to let me know how I did. Subscribe to the channel for more videos just like this one, and leave a comment recommending what you would like to see next. If you want to support my work even more, you can become a Patreon member to receive exclusive benefits. Alongside my tutorials, I also create Unity assets that you can get access to. Links in the description of the video. Thank you for watching. See you in the next one.